So our next presenter has been working on ZFS for about a year, and you might have heard of him doing the work on the zpool checkpoint project. So please welcome Serapheim Dimitropoulos, who is going to talk today about optimizations of the ZFS allocator and the space maps.
Thank you, Pavel. Can everyone hear me well? Yeah. Okay, I'll take that as a yes. So, hello everyone. My name is Serapheim Dimitropoulos. As Pavel said, I've been working on ZFS for around a year at Delphix. And today I'd like to share with you details on a project that I've been working the past few months called the Log Spacemap project. As Pavel mentioned, that's an optimization the ZFS allocation performance. So before we actually go into the internals of this project, I would like to go through some background on how ZFS does certain things. And for some people, that may be, pretty much, you may already have this knowledge, but I'd ask you if you could bear with me for a little bit until we get to the actual details of the project. So, just starting from the very beginning, how ZFS does writes. Well, we have incoming data coming usually through the write system call, and we recall all this data in memory. We periodically sync this data to disk, and as many of you know, we call these transaction groups. Basically, these sync cycles, you can think the writes are single transactions. We wrap them together in a group, therefore the transaction group. And we use these transaction groups as basically the logical timestamps to represent times and event within this ZFS. So, as most of you know, and probably you use ZFS for that, it's a copy and write file system, which means at the block level, we never actually overwrite data. We always mark whatever we have as free, and we allocate our new data somewhere else. And I want to emphasize that because this is true even for metadata, not only just whatever the user asks us to write on disk, but also for any kind of tracking that ZFS does for itself. Another thing that it's important to kind of motivate the problem that we're going to see later is that each sync pass, each TXG basically, is divided into further sync passes. On the first sync pass, we write our user data, and in subsequent ones, we basically update any metadata that need to be changed because we wrote this user data. So let's go into space allocation now. Well, each top-level VDEV from the ZFS perspective is divided into around 200 equal regions called metaslabs. And each metaslab basically represents the ZFS point of view on what is free and allocated in its assigned region of disk. So the first metaslab, let's say we have a VDEV, represents offset 0 to 200, let's say. And the second metaslab, 200 to 400, they're all equal, and basically they keep track of the space. Within ZFS, we represent these metaslabs mainly by two structures. One in-memory structure called the range tree, and one on-disk structure called the space map. And before I go into this, more into how these structures look like, I would like to also emphasize some terminology. So whenever I say that we load a metaslab, it means that we basically read the on-disk structure, the entries on the space map that we're going to see later, into memory, into the range tree. Another thing that I want to emphasize is that in ZFS, we only allocate from loaded metaslabs, basically the ones that the range tree is populated. But we can free from any type of metaslab, loaded or unloaded. So, range trees. This is the in-memory structure that we said that represents a metaslab, and it kind of looks like this. It's an AVL tree where each node represents a free segment, and most of the time, these segments are sorted by offsets, as you can see in this figure that I have over here. Other times it's sorted by size, depending what we're going to look at. But basically, I hope that it's pretty straightforward that this range tree kind of represents the state of the space that this metaslab keeps track of. You can see 1 to 3, blocks 1 to 3 are free, and you see this one node over here, and so far and so on. The corresponding on-disk structure, the space map, for let's say this specific metaslab, looks kind of like this. Spacemaps are append-only on-disk structures of, that have entries of allocations and frees that we do in the assigned space of the metaslab. And you can kind of see that it has the history of the metaslab starting, let's say, from transaction group 10. And we did a bunch of allocation. Let's say we allocated blocks 1 to 5, but later we freed blocks 1 to 3. So basically, the state of the metaslab kind of looks like that. And you can see that the spacemap is not as compact of a representation as the range tree, because the range tree we have 3 entries. They're pretty flexible. But if we want to get the exact same state for that disk, we have to read the spacemap from beginning to the end to actually realize, okay, what is free right now and what is allocated. And as I said earlier, whenever we load a metaslab, we basically have to read this whole spacemap and load whatever current state we figure from it to the range tree. So the longer the spacemap, the more increase the loading time. So once in a while, we condense these spacemaps in order to reduce that loading time. So we have the spacemap that kind of looks like that, and then we condense mainly, we only condense loaded metaslabs because we actually have the range tree available. So we can say, okay, well, obviously the spacemap is getting too long, and if we were to write our range tree as a spacemap on disk, we would actually save space. So once we realize this, periodically we condense the spacemap to something that looks like the one on the right, where we basically look at the current state of the pool and say, like, okay, blocks 4 to 5 and 8 to 9 are allocated, and everything else we assume it to be free. And that's to make the representation of the spacemap more compact on disk. So just to recap, we talked about what TXGs are. The sync passes, the first one being the pass that we are writing the user data, and subsequent ones to update ZFS metadata. We talked about metaslabs. We saw how range trees as spacemaps look like. And I also mentioned that we can free space from any metaslab, loaded or unloaded, but we only allocate space from loaded ones. So, okay, these are all great. What is the problem? Well, the problem comes into play, the problem that I'm going to describe in a bit comes into play in certain pools where we basically have a bunch of files, big or small, and we keep overwriting their data. The problem that I'm going to discuss with doesn't have to do with workflows where we have, let's say, one big giant file and we keep appending space, basically a workflow that you would ingest a lot of data. But even if you have this workflow, I hope that you can still benefit from this talk because we're looking at some very deep technical stuff here. So what's the problem? Well, the problem on the workflow that I just described is the dynamic allocation behavior of the pool over time. And what we've generally seen within Delphix is, after a while, we've touched every metaslab on every VDEV of the pool. And that's because, we overwrite data, we mark something as free, and we move on and we allocate space somewhere else. So after a while that we've touched almost every part of the pool, we have a few loaded metaslabs that we allocate from and may be free, but these allocations, we also have the corresponding frees that are scattered throughout the pool, in all the metaslabs and all the VDEVs, which means that since we are freeing blocks from all metaslabs, we actually have to go to each spacemap and update it by appending a little bit at the end of it. So let's do kind of like a quick arithmetic of, okay, how many IOs do we do just appending to each spacemap? So every transaction group, in every VDEV, we append, as I said, to almost all metaslab spacemaps, so around 200 IOs because we have around 200 metaslabs. And that's assuming that the entries that we have to write into them fit within that 4K block size that we already have made by default in ZFS. And for each update on these actual spacemap structures, we have to also update their indirect blocks. So assuming 2 levels of indirection, we are talking about around 400 additional IOs. And because space maps are ZFS metadata, for redundancy, we keep 2 extra copies on them. So however many IOs we have so far, we need to triple that. So we're talking about around 800 IOs per VDEV each transaction group. So is this actually a problem, though? Okay, we did these calculations, more or less, kind of like a bug on the envelope, to see our ballpark. So is this actually a problem? Well, here is some dtrace output from a Delphix VM that we have, and this from this specific line that we see over here is statistics on one transaction group. So we see on the first column, okay, we started this transaction 0 milliseconds from the previous one, so we started literally exactly while the previous one finished. We wrote around 3 gigabytes of data in around 4.5 seconds, and you can see the rate there all the way to the right. But what's important here is that percentage of time spent in sync pass 1. Now remember that in sync pass 1 we write user data, basically the data that the user asks us to write on disk. And the other 30%, the subsequent sync passes, we're updating metadata, space maps, and basically mostly space maps, to be honest. And you can say, okay, maybe that happened only once because we had like a bunch of changes. But looking at the same VM, we see that the situation is not getting any better. We're actually spending around 20% to 40% of the time going to disk and updating all this like internal state, while all this time it could have gone to actually writing user data. So looking more into each individual TXG and looking at what type of IOs we do. This is data generated by dtrace, and I present them in this way. I hope it's more intuitive, but basically around 37% of our IOs go to write user data. Around 39% is actually triggered by the user data changes. We have to update indirect blocks for the user data and things like that. But what is important here I want to highlight is around 25% of our IOs go to appending spacemap metadata. And these IOs, it's not that we actually utilize all of our bandwidth. As I said, we append a small amount of entries to each space map of all the meta slabs. So what can we do about this? Well, we could decrease the number of meta slabs. Less meta slabs means less space maps, and therefore we will have fewer IOs. But the VDEV size stays the same. So each meta slab will represent a bigger area on disk. And this could lead to 2 issues, because with a bigger meta slab, we'll have more entries, the space maps get bigger, so our loading time for the meta slab increases because we have to load all these entries from disk to memory. And then once all these entries have made it to memory, the range trees can get pretty big, so memory consumption is also an issue with this approach. What about increasing the block size? We said that it's 4K. Maybe if we increase it, we can fit more entries, and basically we won't have to go to disk as many times, and we'll have fewer IOs. It would also speed up the loading time when reading these space maps. But unfortunately, as I mentioned earlier, we write a lot of changes to a few meta slabs and a little to the rest of them. So increasing the block size will actually make things worse because we will have more wasted bandwidth. So here's an idea. Why don't we just not flash all metaslab changes every TXG? Why don't we instead keep everything in memory in 2 new range trees per metaslab, one for unflashed allocations and one for unflashed frees? So basically how this would work is that we'll have some incoming allocations, we will put them into the unflashed allocs tree, incoming frees would go to the unflashed free. if an allocation is already unflasked, which means it's in the unflasked allocs tree, and we need to free it, we basically move it from the unflasked allocs to the unflasked frees, and vice versa if we want to allocate something that's free but not flashed to disk. But we need to write at least something to disk for persistence. So why do we just flash one metaslab every TXG? And let's say for now in a round-robin fashion. So basically, the key difference here is that instead of appending a little bit to each metaslab space map, why don't we just once in a while write lots of changes to one metaslab? So right now, loading a metaslab changes from just reading its space map to reading its space map and applying whatever unflashed allocation and frees we have kept in memory for that specific metaslab. And then the question asks, okay, you have all these changes in memory. What if we crash? We have all these unflashed changes in memory. They're going to be lost. And here's where the log space map comes into play. So for persistence, in case we crash, each TXG we're creating a new pool-wide space map which logs all the allocations and the frees that happened pool-wide, not just for a specific metaslab or a specific VDEV, but for the whole pool. So by writing this every TXG, we still have the persistent state of the unflashed changes per metaslab on disk, which means that after a crash, we can just go and read them and reconstruct all this unflashed state. So, okay, just to recap on the main idea, basically, the idea here is instead of appending to all the metaslab space maps every TXG, we just write one big log with all the changes that we have in the pool for that TXG. And for one metaslab, we flash the two unflashed alloc frees into its space map. So just to give a more pictorial example so people can understand what I just said, let's say that the current transaction group is 10, and we have, 200 metaslabs. Let's say the number is fixed for now, and they were all flashed at TXG10, the one that we just wrote, and you can kind of see their entries. So let's say for people who want to get very detailed on this diagram, Metaslab 1 looks at blocks 0 to 10, Metaslab 2, 10 to 20, and so far and so forth. And at the next TXG, we decide to activate the new log spacemap feature. So what would that mean is that TXG11 or all our new spacemap entries will go to this pool-wide log over here on the left. And then we, as I said, one log, and then we flash one metaslab. So you can say that some entries from the log spacemap actually made it to the metaslab spacemap for this TXG. I hope the gray color is visible here. Cool. So basically, by marking the gray, I mean that, okay, these spacemap entries have actually made it to the metaslab spacemap. So just to go a little bit faster, in the next TXG, we flash metaslab 2. You can see that flashed counter over here. We flashed more changes. We flashed entries from both the log spacemaps made it to metaslab 2. And the same thing can happen for metaslab 3, so far and so forth. So at some point, though, let's say after 200 TXGs from now, we went all the way up until the end of this metaslab array, and we flashed almost all the changes from the log spacemap that was created when we first enabled the feature, which means that this log spacemap is no longer relevant. All these entries have made it here on the right side on the metaslab spacemaps. We call these logs obsolete logs because they are no longer needed, they take up space, and if we crash, we would have to read all these irrelevant entries, therefore the import time after a crash would increase, which is bad. So you could say, okay, once you do one round over here and you go through all the metaslabs, after every flash, you can start destroying each log space map starting from the oldest one. But it's not as easy because, if you add a device, you add more metaslabs. If you remove a device, you take out some metaslabs. There are other issues too. And also, I kind of want to hint later that we may want to flash more than one metaslab. So for dealing with obsolete logs, we want kind of like a more generic algorithm to know when is it okay to get rid of a log. So the algorithm is kind of like this. We keep a list of all the metaslabs sorted by the TXG that they were flashed. Basically, up to what TXG do their space maps have entries from. So in the beginning of the list, we have like the oldest flashed, which would probably, will be missing a lot of entries on the space maps. And at the very end, we'll have the most recently flashed, the one that we just flashed, and it should be fine for now. We also keep a list of all the logs sorted by TXG, which is also the TXG of the changes that they contain. So each transaction group, we basically take out the oldest flashed metaslab, we flash its changes, we put it at the end of the release because we just flashed it, and then we look at the next one and say, okay, the oldest flashed metaslab right now has changes up to TXG, let's say 20, which means that all the transaction groups before that, all the changes from these transaction groups have made it to the metaslab space maps. Therefore, it's safe to destroy these logs because their changes have made it to the metaslab space maps. So yeah, that's more or less the idea of dealing with obsolete logs and basically making sure that we keep our logs within like a certain size. So with these changes, another thing that we might want to reconsider is the spacemap block size. As I mentioned earlier, currently the spacemap block size is 4 kilobytes, which it made sense in this previous state of the world where we were writing, little changes to each space maps, and all these changes were scattered throughout the pool. And for loading the metaslabs, it's an okay size depending on the metaslab size that you have. But now that we're introducing this log space map, reading a space map with like a 4 kilobyte block size, it means that we'll have to do lots of IOs going back and forth on disk. So we propose bumping up the size a little bit to 128 kilobytes, which should make a lot of sense in the new world because we have a few appends instead of like a few large appends actually, instead of like many small appends, one for the log space map and one for the metaslab that we're flashing. It should also decrease the loading time for metaslabs and also the recovery time when we have to go to disk and read all these log space maps. And I kept talking about crashing. I also want to mention what we're thinking about doing when we export and import the pool. Well, at some point, we have all this space in memory with the flash changes, and we're thinking that maybe it's better if we just flash all the metaslabs during export, so all these range trees make it to the metaslab space maps. All these unflashed allocation trees make it to the metaslab space maps, so we don't have to read it at import time. Because reading these changes at import time, as we said, some entries are irrelevant. No matter if the log is completely obsolete or some entries are obsolete, we still waste time reading these entries and going to disk. So it's obviously a lot better to flash everything and not having at export and not having to read anything at import than doing the opposite of not doing anything at export and reading everything for disk at import. And at that point, I was planning on giving some performance evaluation results. Unfortunately, I completely underestimated how much time it takes for a pool to get fragmented, especially when it's very big. So I apologize about that, and hopefully I'll have some results for you that I could post online for this. So this is more or less the main concepts behind the log spacemap project. There's still one unanswered question, which I kind of hinted earlier about the flashing algorithm. Basically, how many metaslabs do we want to flash? Because we may have some problems flashing only one metaslab every TXG. And that is, if we have a lot of unflashed changes just like hogging up memory in the unflashed allocs and frees, well, that's not good. And also, if our workload has like all these incoming changes where, we have to put a lot of entries in the log space maps. Well, the reconstruction time, if we crash, is going to take a performance hit because we have to read all these things from disk in order to import the pool after a crash. So we are still, as I said, it's an open question on how many metaslabs do we want to flash each TXT. And the things to consider here are, as I said, the reconstruction time. We want to make sure that our log space maps don't have a lot of blocks on them. So if we crash, actual reconstruction of the unflashed state won't take as much. The memory usage that I just mentioned earlier, the smoothness and the consistency of the behavior of our flashing algorithm, because we don't want to get into some state where we're like, okay, we are running out of memory, or the logs are too big, so we flash more metaslabs, but the user is not actually doing anything at that point. And we have these spikes in performance, even though there is no, activity has stopped happening in the pool. So we want something that's easy to reason about in terms of performance. And also, on the other side of the coin, we don't want to flash a lot of metaslabs because, we just increased the block size, and also we don't want to get back to that old state with, we don't have a lot of changes pending, but we're still flashing a lot of metaslabs, going back to the previous problem of putting a small amount of entries in each space map. So yeah, this is more or less what I have specifically for this project. There are some more resources that you can read, and to get more familiar with the subject, also feel free to ask us on Slack about any questions that you have with this ongoing project, or email me or tweet me. And how are we doing on time, Pavel? Okay, cool. So since we're doing well on time, before I take questions, I also want to add some more content that I have, and this is basically an improvement that we did into space maps for scalability, which actually enabled the log space map feature to happen. So at this point, if you've spaced out and you look at me and I kind of look like this, and you're like, okay, this guy talking about his space maps, bear with me for 5 more minutes, because I think that the change that I'm about to talk about is pretty cool. Specifically, I want to talk about the current Spacemap encoding, and I also brought the picture from the previous slides just to kind of emphasize that, okay, the spacemap, each spacemap entry kind of has like some more fields. You can see on this bright yellow here, we have a debug entry where we have the action, we allocated some space, the sync pass, and the transaction group. And on the white background, we have the non-debug entries. We distinguish them with this 1 and 0 right here, where we're saying, okay, from which offset does this allocation or free start, and what's the length of it in terms of like how big is that segment? That's what the run means right here. So what's the problem with this encoding so far? Well, if you're using 512-byte addressable storage, which is basically the minimum, I think, that we can ZFS can work with, these 15 bits in the run length can only represent a 60 megabyte region of a segment. Also, looking at the offset, these 47 bits, assuming again the 512-byte addressable storage, means that a spacemap can address up to 64 petabytes. The first problem makes it hard if we want to store a large region of space in a spacemap entry. So for example, if you free a file that's 1 gigabyte and it's contiguous on disk, the range tree is going to have only one node saying from 0 to 124 or whatever. But the spacemap will actually need to use 64 entries because it can only do 16 megabyte regions at a time. Also, for problem number 2, it basically limits the maximum size that can be addressed by the spacemap for a top-level VDEV, which means that if you would like to use a spacemap for to track something VDEV-wide or pool-wide, as we said for the log spacemap, you can only address up to 64 petabytes, which is pretty limited because I'm pretty sure there are so many people in this room that have pools that are more than 64 petabytes. So yeah, this slide more or less explains that, oh, we already have some features that are using VDEV-wide space maps, like device removal and the storage pool checkpoint. And this means that if you want to use these features, with the current space map, your top-level VDEV should be up to 64 petabytes, but no more. And again, if you want to use the log space map project when it's completely done, you need to do better than that because, as I said, people have larger pools than 64 megabytes. So this is the new Spacemap encoding. As you can see, we kept the two old types of entries just to be backwards compatible. And we introduced a new two-word entry, which you can basically distinguish by the first 2 bits. We also added some padding just in case something changes in the future. We want to add more types of space map entries and things like that. But there are 3 things to note here. First one is that the run went from 15 bits to 36 bits. The offset went from 47 bits to 63 bits. And we also have this new field for a VDEV ID, which is important because, as I said, it would be nice to actually know, for the log space map, for example, it's good to know where this segment came from which VDEV. So now with these new changes, we can represent a 35 terabyte region on disk, and we can address with the lowest maximum, with the lowest byte addressable storage, we can address up to 4.7 zettabytes. Also, for anyone who is concerned about, okay, but now you're using 128 bits instead of 64 bits, you can calm down because we still use single word entries to represent regions that are less than 16 megabytes, or for other features, specifically for meta slabs, that they probably don't need the VDEV field, for example, when they write. And we use the double word entries for anything else. So next time you hear about people talking about space maps, you can just jump in and be like, okay, now with this new cool change, we have like a lowest maximum size of 4.7 zettabytes of stuff. Yeah, I think I overused this meme, but yeah, I can take questions now.
In your initial workload analysis, where you're showing the overhead post-pass 1, is that based off a variety of workloads or a single workload?
It's basically, I wasn't, for this specific VM. Oh, yeah, I'm sorry. The question was, for the examples that I showed earlier, was there a specific workflow that what type of workload was that? That's the question. And the answer is that I don't exactly know. I know basically what this VM is used for is to provision other VMs. So we know that we allocate a lot of space and we override certain parts within it, and occasionally we free all that space, and that kind of triggers all these situations that I mentioned where we have a lot of overrides and then we have like big frees, and as I said, we've touched the whole pool after a while, so all these frees are scattered around the pool.
A worst case example in your mind, or was it? I mean, the question I guess was, is this a generic? Often are we having this much overhead, or was this a situation that shows up?
It shows up pretty often because, assuming that your pool has lived long enough, you would still get into that situation where you've touched the whole pool, and every time you need to free something because you need to allocate something, you're gonna touch other meta slabs that they're probably not loaded.
When the pool becomes very
fragmented. Yeah, I can see that.
Exactly.
Yeah, so maybe that's really the answer.
Oh yeah, okay.
You pretty much always get into a situation where you're like freeing a little bit from every meta slab, but like how bad that actually is in practice. Like you showed
At 24, yeah.
all of your IOs are like that. You're pretty much going to get into that situation regardless. But if you have enough big chunks of free space, then the aggregation will mean that the actual performance impact is relatively low. But on this system, it's pretty fragmented, so that's why we saw the actual performance impact in the like
Any other questions? Oh, up there.
Pretty much the same question. So all this is applicable only when you have a heavily fragmented code, right? So by default, ZFS tries to use same metaslab within a video as much as possible, unless it is fragmented, doesn't have enough space, then it moves on next one. Right? So on a system which is not heavily fragmented, how much of impact does this feature have?
Well, oh yeah, I'm sorry. So the question is, this sounds more of like a thing for more fragmented pools, and how does this actually improve the situation in pools that are less fragmented? Did I get the question right?
Trying to understand the impact of it. So to understand correctly, the metaslab usage itself is like the allocation algorithm tries to stick to a single metaslab as much as possible, right?
Yeah.
Means your IO for that particular pool or Spacemap or for every transaction is going to be only for one particular metaslab, which could be contiguous and a large array.
Yeah, but so basically you're saying here that, okay, we have one meta slab that is loaded and we allocate from it and we allocate these contiguous spaces. So why would we go to other meta slabs?
Yeah, so even if it's not contiguously allocated, even if it's scattered across that metaslab, since your Spacemap rights are going to be appended rights, and for a single
Oh, it should be fairly efficient just doing, yeah. And that makes sense. Again, I think that after some time has passed, and let's say you keep writing, right? And you did your allocations, you use that metaslab. After a while, you're gonna start using some other metaslab. Is that correct? Well, once you're running out of space on this specific one. And then you're gonna do the same for the next metaslab and the next metaslab. And after a while, you'll have used all of them. That's regardless of if you are actually using, if you are actually increasing capacity or not, right? This is.
Yeah, I can understand from a fragmented pool perspective, if you use
Yeah.
that fact.
So I believe that even if fragmentation is not very big, I think that we can still save in the number of IOs. But that said, I'm not sure of how big of a benefit you would actually see at that point.
Yeah, as a matter of fact, in your scenario where you're saying you really have one metaslab, it's very similar to having a pool-wide space map. So the performance implications of what we're trying to accomplish here would be very, it's probably what you're already seeing. You have one metaslab that's being repeatedly used.
Have you considered opportunistically flushing your metaslabs? Right now, you're thinking about how many metaslabs to flush in sync phase. You commented that, you don't want to have unexpected IOs, but on the other hand, it seems like you often have situations where you have a sync phase where you have available capacity where you can say, "Oh, let's dump a bunch of metaslabs out here in this opportunistic period."
Yes, so the question is if we've thought about basically like once in a while try to put some more IOs even though we don't need to flash as many metaslabs, flash a little bit, even though there's not a lot of activity going on. And that's definitely something that we're thinking in. Specifically, the main problem is that you have a lot of changes, and you write a lot to the log space maps, and then you kind of stop, and then maybe a little bit later you start again, and maybe you stop. But basically, that drop later is something that we would like to. The trade-off is basically trying to smoothen out the IOs like over time, and basically trying to guess, okay, because what we're trying to achieve here is destroying the oldest logs, right? The obsolete logs. So it's kind of like looking, okay, how many metaslabs do I need to actually flash until that time? And based on the workload that I've seen so far, should I flash maybe a little bit more just to make sure that later, I'm better off? So yeah, this is basically the main problem that I'm working on currently on that project. But yeah, I'll be interested to talk more about it if you have any ideas. Okay.